Good morning, good afternoon, or good evening. I'm Cam, and welcome back to Quick IB Chem with Cam. Today, we're going to be talking about IB chemistry, SL and HL, on topic S2 with the following subtopics. There's a lot of material to recover and recap, so let's head straight on. So the first thing that we're going to talk about are ions. Ions form when atoms gain electrons and become negatively charged, anions, or lose electrons and become positively charged, cations. Metals form cations, and nonmetals form anions. Elements want a stable octet, which just means 8 electrons in the outermost shell, except for hydrogen, boron, and beryllium. Hydrogen only wants 2, and boron and beryllium are satisfied with about 6. Magnesium is in group 2, has 2 valence electrons, so it forms Mg2+. Fluorine is in group 17 and forms F- because it has 7 valence electrons and wants to get to that stable octet. Anions are related to acids, often by hydrogen. For example, hydrofluoric acid, a strong acid, is vaguely similar to this ion, except it is just missing a hydrogen atom. So these are your polyatomic ions. These are ions that you must know. There are 7 of them. Know that how all the oxidant ones and 8. So if you're struggling with remembering all of them, I'd use that as a crutch. Another important thing that's going to carry on to the rest of this unit is electronegativity. Electronegativity is the ability for atoms to attract electrons in a bond. That increases across period and decreases down a group. Increases across period because there are more protons. Decreases down a group because there are more energy levels. Electrostatic attraction, if you see this on the exam, don't freak out. This just means the pull between negatively charged and positively charged particles. Now, ionic bonding and its properties. Ionic bonding is the first type of bonding we're going to talk about, and it occurs when there's a high electronegativity difference between metals and nonmetals, except for the noble gases. The metal effectively transfers its electrons to the nonmetal and forms ionic compounds with ionic lattice structures, which are specific structures that are super strong and with a high melting point and boiling point. Ionic compounds are neutral because the charges balance out, so while their components are ions and charged, the compound is not. You can name ionic compounds by keeping the name of the cation and changing the name of the anion to ending in "ide", like sodium chloride. So an example of how ionic compounds are neutral because they cancel out. Na plus Cl minus forms NaCl, or another example, Mg2 plus N3 minus form Mg3N2. If you're ever struggling to create a formula for an ionic compound, don't worry. All you have to do is swap the charges of the two ions. So basically, the 2 plus, the 2 from the 2 plus of the Mg is going to go here, and the 3 from the N from the nitrogen is going to go here, and that's how you get your Mg3 and 2. That's a little trick that might save you some time. So this is an ionic lattice structure. Ionic lattice structures are known because the ions are bonded or completely bonded to all opposite charged ions, which maximizes the electrostatic attraction. Lattice enthalpy is the measure of the strength of a lattice, and it is highest or strongest when there is a small atomic ionic radii and a high charge for the cation and a low charge for the anion. High charge means that it's going to have a lot more protons per electrons, and low charge means it's going to be highly electronegative and has a higher protons to electron charge ratio. The ions in ionic lattices are bonded to a fixed number of opposite ions called the coordination number. So, for example, if we look at this chloride ion, we can see that its coordination number is 4 because there are 1, 2, 3, 4 sodium ions bonded to it. Now, for properties, ionic compounds have a high melting boiling point, are brittle, are more soluble in polar solutions like water, and they conduct electricity when they are molten or aqueous. So the next type of bonding we're going to talk about is covalent bonding. Covalent bonds occur when there's electrostatic attraction between pairs of electrons and nuclei, effectively sharing the electrons instead of transferring. Covalent bonds can form with up to 3 pairs of electrons. There are single bonds and double bonds and triple bonds, but you have to remember that double bonds and triple bonds occur only between carbon, nitrogen, oxygen, phosphorus, and sulfur only. Covalent bonds are where both electrons Covalent bonds where both electrons come from a single atom are called dative covalent bonds, or coordinate bonds. Bond polarity. Bonds can be polar or nonpolar depending on electronegativity differences. If there is a high enough electronegativity difference, this creates dipoles. One side of the dipole is partially positive, and one side of the dipole is partially negative. And this is within the molecule and between two atoms of the bond, because it's bond polarity. For properties of solubility, polar molecules like dissolves like. So polar molecules dissolve polar molecules, and non-polar molecules dissolve non-polar molecules. So bond polarities are going to coalesce into molecular polarity. Molecular polarity is based on molecular geometry as well. So the dipoles either cancel out or not, making a molecule overall non-polar polar respectively. If you had a dipole going up and a dipole going down, those two would cancel out. Molecules are held together by intermolecular forces called IMFs. These include, that you have to know, London dispersion, induced dipole, dipole, and hydrogen bonds. Bonds differ in length and strength. Generally, single bonds are going to be the weakest and longest. We can see a single bond between carbons has a bond length of this, or 0.154 nanometers, and a bond enthalpy of 246 kilojoules per mole. Double bonds are stronger and shorter than single bonds. You can see the difference here, where the bond length is shorter and the strength is higher. And triple bonds are going to be the strongest and the shortest. Obviously 0.12, a lot smaller than 0.134 or 0.154, and has the highest bond enthalpy sitting at 830 kilojoules per mole. So in order to better understand single, double, and triple bonds, we need to talk about molecular orbitals. As electrons exist in atomic orbitals, covalent bonds are more accurately represented by the overlap of these said orbitals. This overlap creates what's called molecular orbitals, kind of like specific bonds. So these two specific bonds that you have to know are sigma bonds, which are single bonds that occur from the head-on overlap of S on S, S on P, or P on P orbitals. These are along the internuclear axis. And the internuclear axis just means if you were to draw a line horizontally between the nucleus of an atom, that's where it happened, or that's the internuclear axis. So here, where the blue represents S, the red represents P, and this is the S on the P. We can see that if this is assumed to be the nucleus, then we can see that a line between them forms. That's the internuclear axis, and they occur head-on and create this sigma bond area. And these two hydrogens now become bonded as with the sigma bond in the middle. The same thing happens with the head-on overlap of p on p orbitals, where you have these two fluorines that bond together to make an overlap with this sigma bond represented by this large structure. And then you can see the same thing happen with S on P. Now the second type of bond we have to talk about are pi bonds. Pi bonds are your double and triple bonds. They occur from the vertical or sideways overlap of orbitals. I like to think about it as sideways, but it's debatable. And they're only for P on P, for IB. That's all you have to know. They occur above or below the internuclear axis. So, as we can see here, there's a vertical or sideways overlap between two p orbitals, to where you have these regions created above and below the internuclear axis, where these electrons will stay bonded. Now, it's important to know that pi bonds, because they're above and below the internuclear axis, are going to be weaker than sigma bonds. Now, you might be a little confused about this because double and triple bonds are stronger than single bonds. But what you have to understand is that these sigma bonds are specifically the first single bond that occurs in a molecule, right? The double bonds are, when you refer to double bonds, like in the last slide where double bonds were stronger than single bonds, it refers to both the sigma bond and the pi bond together, right? So here we have a double bond where you have the sigma and the pi bond represented together, and a triple bond where you have the sigma and the two pi bonds represented together. However, individually, pi bonds will be weaker than sigma bonds because they're not along the nuclear axis. So now that we refreshed on that, we can also refresh on intermolecular forces. Intermolecular forces occur between the molecules, that's why they inter, and the lowest on our list is going to be London dispersion LDS. Now, these occur in all molecules, but they are the only IMF for nonpolar molecules. Lund dispersion forces are the electrostatic attraction created from random movement of electrons or an induced dipole, but only instantaneously. So if all the electrons move to one side of the atom or compound at one time, one side's going to be partially positive, and one side's going to be partially negative, as if it had a dipole or was polar. So London dispersion forces are going to increase with molar mass and increase with surface area. Make sure you know that. Third, dipole-induced dipole forces occur when a polar molecule creates a dipole in a nonpolar molecule, as charged ends of polar molecules tug on the electrons. So the partial positive end of a polar molecule is going to tug on the electrons of a nonpolar molecule, bringing them to one side and therefore making a dipole in that nonpolar molecule, even though generally it is not polar. The second strongest, is dipole-dipole forces. These are when polar molecules are attracted to one another because of their dipoles. So it's just two dipoles attracted to one another because of their partial positive and partial negatives. Dipole-dipole forces increase in strength with the polarity of the molecules. Now, for the king of intermolecular forces, hydrogen bonding. These are not chemical bonds. Please do not ever believe that these are chemical bonds. I will cry. So, hydrogen bonding occurs when hydrogen is covalently bonded to small, highly electronegative atoms like nitrogen, oxygen, or fluorine. So, electronegative elements makes hydrogen highly partially positive, and it gets attracted to the lone pairs which have a negative charge in neighboring molecules. And that's why it's highly partially positive, because it has to be bonded to highly electronegative atoms. These are basically just super dipole-dipole forces. And hydrogen bonding is the reason why water has a much higher boiling point than other hydrides or hydrogen covalent compounds. Now that we understand intermolecular forces and the bonds themselves, we can talk about how to represent these bonds with Lewis/electron dot structures. So I'm going to be referring to them as Lewis dot structures. Lewis structures show all the bonds and valence electrons in a structure. Bonds are represented with lines, and lone pairs can be represented with dots or crosses. I prefer dots. Steps for Lewis structures. First step is to find the central atom. There might be only one in the formula, depending on the difficulty of your exam. But a better understanding is that's going to be the least electronegative. So after that, you draw all the atoms that are connected to that central atom. And then you have to subtract bonded electrons from the valence electrons of all the atoms combined. And once you have that, you use the leftover electrons to satisfy the octet rule for atoms, unless it's hydrogen, boron, or beryllium, because those are the exceptions to the octet rule that we know of right now. And if there are no electrons left to satisfy the octet rule, you can form double or triple bonds through CNOPs, or with only CNOPs elements. If you are drawing an ion, make sure to put it in brackets with the charge in the top right. So as an example, ammonia, or NH3, would have a Lewis electron dot structure like this, where you have nitrogen bonded to 3 hydrogens with electron dots in the top. Always make sure that your hydrogens only have one bond, because they can only have 2 electrons in their one energy level at a time. And if we look at its ion, ammonium, we can see that it's lost the lone pair and instead bonded with another hydrogen. We have it in brackets with a 1 plus charge on the outside. Remember that this is a polyatomic ion that you need to know, so I thought it'd be a good example. If we were to go through the steps for this, we can see that we knew nitrogen had to be in the middle because it had hydrogens, and so nitrogen is going to have 5 valence electrons, hydrogen is going to have 1 valence electron. So we have 5 valence electrons for 1 nitrogen, and we have 1 valence electron for 3 hydrogen. So that 5 plus 3 is going to equal 8. Now, because there are 3 bonds, that means there are 6 bonded electrons. So 8 minus 6 equals 2 is what we're left with. And to satisfy the octet rule, we put these extra 2 electrons on ammonia to get 0. And we can see with the ammonium, we do the same thing, except we just subtract by 1 electron, and we subtract by 1 electron because 1 plus means that we've lost an electron. So we have 8, and then we have 8. They have 4 bonds, 8 bonded electrons to make it 0. And everything's happy. Now another example is going to be boron trifluoride, where we can see that boron, least electronegative, is going to be bonded to 3 fluorines, and after bonded, those are going to after bonding those, we're going to subtract 6 electrons, and we're going to be left with however many there are, and we're going to put them on all of these fluorines because they're the most electronegative, and they're going to want those first. Now, notice how boron does not have any, does not have a fourth bond or any electron pairs to satisfy its octet rule. This is because it's an exception, and this is just how it's drawn. So, getting to more HL topic, and hopefully this is a little bit easier review than the other orbitals, other HL stuff. Delocalization and resonance structures. So delocalization is when electrons are shared over multiple atoms, and it's the basis of resonance theory. This is often because of alternating double bonds or multiple places for a double bond to occur, and it's the more stable for the compound. So instead of forming one double bond and one single bond, it's actually just going to form kind of a halfway point. So the most prominent example of this is going to be benzene or C6H6. Resonance structures are when there are multiple places to put a double bond to satisfy the octet rule. These are drawn as Lewis dot structures. You must draw all resonance structures with arrows in between, and resonance hybrids will be specifically asked for. Now, carbonate resonance structures include carbonate with a double bond to the oxygen, carbonate with a double bonded to the oxygen at the bottom, and carbonate double bonded with the oxygen to the right. Now, all of these are technically correct, because we'll talk about formal charge later and how you choose the best resonance structure to draw, or the best Lewis dot structure to draw. But these are how you would show them. But what actually happens is a resonance hybrid, where the delocalization of electrons causes them to be shared over multiple atoms. This is represented by these half bonds, or these kind of dotted, these segmented bonds, where we have 6 electrons being shared over all of these. Now, resonance hybrid is what actually happens. Electrons are shared over multiple atoms. Now, supporting evidence for this is bond lengths, because resonance hybrids, or resonance theory, states that the bond lengths will be in between a single bond and a double bond, because these electrons are shared rather than just being single bonds or double bonds. Ozone, or O3, is also a good example if you want to look at more resonance structures or resonance hybrids. So, formal or resonance structures, I apologize. So, talking about formal charges are used to indicate the most stable structure when there are multiple correct Lewis structures. Each formal charge applies to individual atoms. However, formal charge incorrectly assumes all atoms bonded have the same electronegativity, but they help us determine which structure is going to be most stable and therefore most favored. Formal charge close to 0 is preferred by the structure, and there's a formula for formal charge. In case you forgot, it's going to be valence electrons minus the number of bonds plus the lone electrons of that atom. So here we have an example of sulfur dioxide, where I drew one of the resonance structures of sulfur dioxide, and I drew a sulfur dioxide with 2 double bonds. Now, if we look at this, both of these models satisfy the octet rule for both of these, where oxygen is going to have 8 electrons, and sulfur is going to have 2 electrons, 4 electrons, and 8 electrons, and this is going to have 2, 4, 6, and 8 electrons. So all these are happy. The same thing occurs here, where instead of having a lone pair on it, sulfur forms 2 double bonds with the oxygen. But we can use formal charge to deduce which is more correct. So first, you're going to have to take the formal charge of all the atoms in whatever compound you're drawing. So formal charge of the first oxygen atom is going to be 6 minus 1 plus 6, which equals negative 1. Formal charge of sulfur is going to be 6 minus 3 plus 2, which equals plus 1. And formal charge of the O2 is going to be 6 minus 2 plus 4 equals 0. We can see oxygen is going to have 2 bonds for lone electrons. 6 minus 6 is 0. And the formal charge of the other drawing is O1 is going to have 6 minus 2 plus 4 equals 0. Sulfur is going to have 6 minus 4 plus 0 to equal plus 2. And O2 is going to have 6 minus 2 plus 4 equals 0. Now, even though these are both plus 1 and minus 1, and this one's going to be a plus 2, the more of the atoms in the second structure have a formal charge of 0 and is therefore preferred. So it's whatever gets you to the most 0 formal charges. Now, earlier we talked about the delocalization of electrons, and we talked about benzene being a good example, and benzene is something you're gonna have to really know, stretch in on. So benzene is C6H6, and it's a cyclic carbon compound with a ring structure. So it supports resonance theory because its properties are only explained by resonance theory and the delocalization of its electrons. So if I go here and get a pen, I don't like this color, let's go blue. So this is what's called the Kekule structure of benzene. Now this is where the double bonds between carbons are alternating, right? And so you might see the Kekule structure drawn like this or drawn like this. It's always going to be this hexagonal shape with alternating double bonds. Now, there's a lot of evidence from benzene on why resonance theory is true. So first, we're going to have to look at the bond lengths. So earlier we talked about resonance hybrid. Resonance theory is going to be resonance hybrids are supported by bond length. Well, this is an example. All carbon-carbon bond lengths in benzene are equal and intermediate in length between single and double bonds. This would not happen in the Kekule structure because this bond length isn't going to be the same as this one unless the electrons are shared between all of these carbons, right? And so because they're between single and double bonds, that's only further supports this theory, as these carbon atoms are taking on extra delocalized electrons, but not fully, as in a bond. Excuse me. Now the delta H of hydrogenation for benzene is another property that can only be explained through delocalized electrons. So delta H of hydrogenation is basically just the energy released or that you have to put into in order to have benzene, be fully bonded to hydrogens at every given area or every given point. So based on the calculations of 3 double bonds, the theoretical value for its hydrogenation would be negative 362 kilojoules per mole. And the experimental value is actually a negative 210 kilojoules per mole. So because it releases a lot, remember that if delta H is negative, that means it's an exothermic reaction, and you're releasing energy. Now, because it's releasing less energy, that means there's less energy stored. So therefore, the actual structure of benzene has to be more stable than the Kekule structure because there's less energy to release. This energy is called the resonance energy or the stabilization energy of benzene. Now, the type of reactivity, benzene is not often undergoing addition reactions and is more likely to undergo substitution reactions. Now, you might think this is weird because we said that the delta H of hydrogenation, where you add all these hydrogens, is actually exothermic and releases energy. But note that this is only because the activation energy is extremely high for this reaction. And so, even though this is more stable, it requires a lot of energy to overcome the activation energy from the stability of the delocalized electrons in that ring. So because benzene has delocalized electrons, it has a higher activation energy and is more stable. Now, addition reactions are energetically not favored as they are involved disrupting the ring of delocalized electrons, as we can see with that high activation energy or delta H of hydrogenation. And the resonance energy would have to be supplied in the product that the delocalized ring of electrons would be less stable. But benzene can instead undergo substitution reactions that preserve the stable ring structure. And now how we relate this one to this one, because if it didn't, it'd be less stable, as explained by the negative 262 kilojoules per mole, whereas if it had the delocalized electrons, it is more stable. Now, for its isomers, as benzene is a symmetric cyclic molecule with no alternating single or double bonds, 2 bromine atoms can replace hydrogen atoms in only 3 possible configurations. We have 1,2-dibromobenzene, 1,3-dibromobenzene, and 1,4-dibromobenzene. Now, this would not be possible because the alternating double bonds restrict the areas where we can add these bromines. For example, you want to be able to add a bromine here or here, right? But you can do that with its actual isomers. which suggests that these electrons are delocalized. Now, often in structures, if this is the Kekuler structure of benzene, this is going to be probably more so the preferred structure of benzene that you'll see drawn, where it's a hexagon with a closed circle in the middle, or you might see it with these dotted lines. Now, hybridization is another part of covalent bonds that we have to understand. Hybridization occurs due to electron repulsion. The electrons want to be equidistant from one another as far away as possible, right? Because electrons repel. So this means that they also want to be equal energy if they want to be equidistant. To do this, atomic orbitals combine or hybridize. This often involves unpaired electrons. And there are three types of hybridization that you need to know for IB. sp3 with methane as an example, sp2 with ethene as an example, and sp with ethyne as an example. Now, sp3 hybridization occurs as an s orbital combines with three p orbitals to make four equally matched sp3 orbitals. There are more like p orbitals than s orbitals, and they occur when there are four electron domains in tetrahedral geometry. sp2 hybridization occurs when a singular s orbital combines with two p orbitals to make three equally matched sp2 orbitals. It's more like p than s, and occurs when there are three electron domains for planar geometry. sp hybridization, the last one you need to know, is an s orbital combines with a singular p orbital to make two equal orbitals. The middle p and s. That occurs when there are two electron domains with linear geometry. Now, some hybridization examples. Let's take methane, our sp3 example. The typical atomic orbital structure of methane is going to look like this, where you have carbon before bonding to methane, right? It has two electrons in its 1s, two electrons in its 2s, and two electrons in its 2p. Well, it has to be able to bond to those four hydrogens, and it wants them all to be equidistant from each other, have the same bond angles, equidistant, same energy. So what's going to happen is that this carbon is going to excite this electron, and we can look at the glow up of carbon before bonding to methane and right before bonding to methane. If it was daring, then it would be filled up, and kind of defeat the point of showing the hybridization. But we can see that one of the electrons has been promoted into the 2p orbital right here, and this 2s orbital has been raised, and the 2p orbital has been lowered so that they match in energy to create the hybridized sp3 orbital. So they meet, one electron goes here to fill this up, and then they meet in the middle. So now you can take the electrons from each of the hydrogens and make equal bonds. And then 1s remains the same. Now for ethene or sp2 hybridization, basically what's going to happen is we're going to take one 2s orbital and two of the 2p orbitals. Note that this is also carbon before, but I have gone ahead and excited one of the electrons into the 2p orbital. And that's going to make a hybridized sp2 orbital. The other 1s is still there, but it's redundant to show here. And now you have the 2p orbital. Well, what's this 2p orbital going to do? Well, it's going to go and it's going to make the double bond that we have right here, or the pi bond that we have right here between the two carbons. Now, our last example, ethine, is going to be sp hybridization, right? So if you look back, 1, 2, 3, 4, 1, 2, or 1, and then 1 plus 3 is 4, and then 1, 2, 3, 1 plus 2 equals 3. Just in case that wasn't clear, probably was. I apologize. But here we're just going to take a 2s orbital, a 2p orbital, smash them together, and we're going to get sp hybridization with two leftover 2p orbitals. And what are those going to do? They're going to do the exact same thing, form two pi bonds. And that's how we get these guys. Make it make sense. Allow them to connect with one another. When you form a groundwork and a basis for how these processes work, it's a lot easier to imagine them. So next we're going to refresh upon valence shell electron pair repulsion theory. Also called Vesper theory, this is used to predict the shape of molecules based off of their electrons. Now electrons, due to all having negative charges, want to be as far away from one another as possible because they repulse each other. And electron pairs can create electron domains either through bonds or through lone pairs. So both these are going to create what are called electron domains, which is areas where these electrons inhabit. Now, electron domain geometry is dependent on just how many electron domains there are. While molecular geometry is more specific and depends on if those electron pairs are lone pairs or bonds. Because they are found in the same region along the same axes, double and triple bonds do not count towards new electron domains, i.e. a single bond will create the same electron domain as a double or triple. So here's a chart of all the SL knowledge, except for hybrid orbitals, that you need to know for these geometries. So I would recommend finding a chart that works for you and using that to review, because these charts are the best where I can show you, or the best way I would recommend reviewing for how these molecular geometries work. Notice the electron geometry, linear, trigonal planar, and tetrahedral, is separate from molecular geometry, linear, trigonal planar, bent, tetrahedral, trigonal pyramidal, and bent. Now, another thing I want you to consider is that in trigonal planar, as we go from 3 bonds to 2 bonds with one lone pair, we drop about 2 degrees. And for tetrahedral, if it's 109.5 and one of them becomes a lone pair, it's going to drop to 107, and if it's bent, it's going to drop to about 105. Now, remember that all these are approximations. A good rule for if you can't remember the electron or the bond angles of all of these are bond angles, right? So this is going to be 180 degrees, it's going to be 120, then it's going to be 118 between all these. Tetrahedral is 109.5. Notice how it's three-dimensional. Trigonal pyramidal, same thing, and so on. So electron pairs, generally, as you add them, are going to subtract your original electron domain geometry by like about 2 degrees. And if you're ever asked a question about this on the IB exam, don't worry about having the magic number. They're all going to be ranges, unless it's a multiple choice question and just ask you straight up. So notice how we can relate the electron geometry to the hybrid orbitals, hybridization that we talked about earlier, where each of these represents one of these hybrid orbitals. For more explanation, this is going to have sp2 is going to have 3 bonds and needs to have 3 equidistant bonds. Well, it's going to make sp2. And bent is typically going to create a resonance structure, and so it's going to be hybridized between those, and it's going to need sp2 hybridization for that. I hope that makes sense. Hope I didn't confuse you. If it does confuse you, I'd recommend just looking it up. It is not often, I believe, that you'll have to explicitly explain why these are hybrid orbitals. But you should remember that these hybrid orbitals are often going to occur from these geometries and with the delocalization of electrons. So for HL, in the HL chart, you also have to remember up to 6 electron regions, right? And we can see the same trend right here, where you're going to lose about 2 degrees per molecular or per lone pair added. You don't have to know the hybrid orbitals for these because you do not learn them. Notice how all these are 3-dimensional, and there's going to be different bond angles between the dimensions, except for linear and square planar. Because in linear, these exist on the same plane, and so it's going to be 180 degrees. But if you look at something like, the trigonal bipyramidal, you can see that there's 120 degrees between the bonds here, and then here and here, and then 90 degrees between these bonds. So notice how I said -2 degrees here. I didn't exactly have the space to put it, but this would be about 88 degrees and 118 degrees. Except for these are 180 degrees, but you want to talk about between the planes. And this also confuses Leah a little bit more. So if I'm not making sense, I promise I've done my research. I just might not be able to formulate it. Now, notice how in T shape you go from about 118 to 178. I believe this is wrong. I'm going to remove this. I apologize. And I believe these are 180. No, that's 100. Okay. We're going to erase that. This should be 178 degrees. This should be 180 degrees. I apologize. Please, ignore that part. So the next thing we're going to talk about are giant molecular structures or covalent network or network covalent structures. Now these are linked by covalent bonds and they form a crystal lattice structure. Ionic lattice, except covalent, and so it's crystal. So these are allotropes. These elements, are going to exist in different forms. Or allotropes are elements that exist in different forms. For example, carbon and silicon, group 14 are the only ones that are going to form this giant molecular structure or network covalent structure. So the allotropes of carbon include graphite, diamond, fullerene C60, and graphene. So notice how each of these have a special hybridization, except for this one, we just assume the graphite sp2 So graphite is going to be a good conductor of electricity with a high melting point. It's a good conductor of electricity because its electrons are delocalized, because these layers of hexagonally bonded carbons are going to slide over each other, right? All of these are only carbon bonded other carbon atoms. And so that's also important to remember. This is going to have 120 degrees between the bond angles. This diamond is also going to have an extremely high melting point, but it's going to be a poor conductor of electricity because it has localized electrons. So instead of being able to slide over each other, they just kind of exist in this space and with a bond angle of 1 and 9.5 degrees. C60 fullerene is also important to remember. You'll often want to call it a shape of hexagons and pentagons formed in a soccer ball shape if you're ever asked to describe how it looks or its geometry. Has 20 pentagons and 20 hexagons. And note, this is not a giant molecular structure because it has a fixed formula, C60, so 60 carbons. Whereas these all just kind of keep on bonding. Graphene is a single layer of graphite. It's 200 times stronger than steel, and it is a semiconductor because it kind of has the properties going on here. But because it's a single layer, it can't fully achieve that delocalization. Another giant molecular structure you need to know is silica from silicon. Silicon bonds into silica, or SiO2, and forms as quartz and sand. It has a giant tetrahedral structure with similar properties to diamond, hard with a high melting point and boiling point. It's a poor conductor because it has localized electrons. So you can see here, each of these silicon atoms is bonded to 2 other oxygen atoms. And this just kind of repeats and repeats forever. So metallic bonding is finally getting to the next type of bonding that we're going to talk about. Metals are made up of a lattice of cations and delocalized electrons, and they flow freely throughout. They are effectively cations in a sea of electrons. This is because they have a low electronegativity and low energy unfilled orbitals. These both combine to give metals a low ionization energy, and therefore the electrons can delocalize because it doesn't take out a lot of energy to pull those electrons apart from those atoms. So alloys are specific or special metals where there are homogeneous mixtures of metals, like bronze, which is copper plus zinc, brass, which is copper plus tin, and steel/stainless steel, which is iron plus carbon, and then to make stainless steel, it's plus chromium. So the different radii and charge of the different metals, warps the structure of the metallic bonding. Alloys are often harder than the pure counterparts, but they have weaker bonding, so like lower melting points, lower boiling points, and all that. So this is a kind of a graph, not a graph, but like a demonstration, a diagram of what metallic bonding looks like. So as you can see, there's a bunch of these metal ions that are acting as cations. These electrons are just kind of floating freely throughout. So they're delocalized, as we had talked about earlier. So properties of metals. They have electroconductivity and thermal conductivity, and they are very good at it because the electrons are free to switch sides because they're delocalized. So, except for group 1 and mercury exceptions, where lithium melts at, kind of sad 180.5 degrees Celsius, and mercury is liquid at room temperature. So, malleability and ductility, which is the ability to be bent into shapes, and ductility is the ability to be drawn out into wires. This is possible because the ions are able to slide over one another and break less bonds than are formed, right? So imagine you're pulling all these apart, you're trying to make a wire, but because these electrons are delocalized and the ions are, able to slide over one another in the C, they just kind of move with it. So luster, delocalized electrons cause metals to have luster. All you need to know. And smaller atom and greater charge equals stronger bonding, right? So this is what you're looking for in metallic bonding. The smaller the atom, the greater charge, the stronger the bond. For HL, for metallic bonding, transition metals, not zinc. Zinc is not a transition metal, and this is because transition metals are metals with an incomplete d orbital. But zinc has a full, complete d10 orbital. These lose the principal energy level s electrons before n-1 d electrons. So, for example, if you were talking about cobalt, cobalt is going to be a transition metal that has I believe it's 4s2 and 3d7. If you form a cobalt 2 plus ion, it's going to lose its 4s electrons and just have 3d7 electrons. Transition metals can form various oxidation states / ions, and they have smaller ionic radii equals extremely strong metallic bond. So we've talked about a lot of bonding, but instead of thinking them as like specific instances, think of it more as a range, right? So this is a new data booklet, and this is called the Van Arkel-Ketelaar triangle. And it's the bonding triangle that shows you, okay, these electronegativities, as we discussed at the beginning, correlate to how ionic, covalent, or metallic some bonding is going to be. So on the y-axis, we're going to have the electronegativity difference between two atoms. And on the x-axis, we're going to have the average electronegativity, which is going to be, the electronegativity, divided by 2. So we're going to start here with metallic bonding. Magnesium forms metallic bonding with an electronegativity difference of 1.3 because it's 1.3, average electronegativity of 1.3 because magnesium's electronegativity is 1.3 and it metallic bonds with itself, and so it's going to be 1.3 plus 1.3, and that's just going to get you 1.3 again, and it's going to be 0 because 1.3 minus 1.3 equals 0. So we can see if we follow the chart, 1.3 is going to get us here and 0 is going to get us here, and so that's going to be in this metallic section. Now, if we were to look at something like lithium oxide, it's going to have an average electronegativity of 2.2 and an electronegativity difference of 2.4. So you're going to go over here and you're going to go up here and go see, okay, lithium oxide is in the ionic bonding part and by like this much. And another example, a polar covalent that's just almost ionic bonding but not quite is aluminum chloride, where you have 2.4 and 1.6 as your average electronegativity and electronegativity difference, respectively. So the whole point of this bonding diagram is to show that bonds exist on a scale and on a spectrum rather than just individual groups. Lastly, the final thing that we need to talk about in S2 is polymers. Polymers are macromolecules held together by covalent bonds. Now they are made up of small units called monomers, and they can form stuff like thermoplastics, which are polymers that are often made from alkenes that can be remolded after heating, which is most plastics, and thermosets, which are polymers that are initially soft, solid, or viscous, but irreversibly hardened, when cured. Some examples you might know or might want to keep in the back of your head are bakelite, polyurethanes, and vulcanized rubber. So elastomers are also another type of polymer that can bend and return to their original shape, and the longer the chain length of the polymer, the higher the strength and melting point. Some important plastic facts are that they are lightweight, strong, unreactive, water repellent, and non-biodegradable, which makes them a problem. And they can solve this problem by making them biodegradable using stuff like proteins and organic molecules. So the process, polymers are created through what's called polymerization. And addition polymers specifically are polymers made from monomers with double bonds. The double bonds break, creating places for them to attach to one another. there's no byproduct in addition polymerization. So the double bonds break, and you just form a bigger polymer. So here's an example of ethene monomers forming into a polyethylene polymer. You can see that the double bond here breaks, and you get, these two. And then because the double bond breaks, well, now there's room on the left and the right for it to bond to other ones. And here's an example, a more specific example of propene forming a polymer. So the repeating unit of the polymer is going to be the monomer that it's made up of. Or the monomer creates the repeating unit. The repeating unit for additional polymers are the monomer without the double bond. So we can see it removes its double bond, and now it can bond with other things. It's very important to note that you have to include brackets or parentheses around these bonds, or brackets or parentheses with bonds going outside of them, to show that the repeating unit bonds from other things. This is very important when you draw polymers. Do not forget the bonding goes outside of the brackets. So HL I'm talking about condensation polymers. Condensation polymers are made from monomers with at least two functional groups. They can be the same one twice, and when they are made, they release a small molecule, unlike addition polymers, like H2O, HCl, or NH3. In the same way that they release a small molecule when they are made, they can be broken apart by adding small molecules in hydrolysis reactions. Now, this is typically done with H2O. So polyesters are condensation polymers made from monomers with carboxylic acids, Cu groups, and alcohols, OH groups. These functional groups form what are called ester links. So we're going to have what's called a benzene 1,4-dicarboxylic acid. And so you see you have your two Cu groups on either side. And then you're going to add that to ethane 1,2-diol. And when these interact, they're going to form an ester link. And so you're going to get polyethylene terephthalate as your polymer. And notice the brackets on the outside to show that it can bond with other things. Don't forget that. So we see here that the Cu group loses in hydrogen, and the HO group is gone from this ethane 1,2-diol, which means that our byproduct is going to be H2O. Now, polyesters are always going to make H2O as a byproduct because of the interactions between this hydrogen and this OH. So now that we talked about condensation polymers or polyesters, we can also talk about condensation polymers continued with polyamides. Polyamides are formed by I believe that's supposed to be diamines. That might be wrong. I think it's diamides. I apologize. And dicarboxylic acids forming an amide link or peptide bond. A prominent example of a polyamide is nylon. So here you have hexane 1,6-dioic acid, where you have your two Cu groups on these sides, and then you're going to add it to hexane 1,6-diamine. So you have your amine. Oh, it is amine. Okay. I misremembered stuff. I apologize. Hopefully that didn't confuse you too much. But it's going to be added to these amines, and these amine groups are going to be your NH2s. And once those combine, you're going to get Oh, yes. Okay, that's also right. You're going to get nylon 6,6, which is a very common condensation polymer that you might want to have in your back pocket. So, as we can see here, what's going to happen is in polyesters, the hydroxide or the alcohol group loses its hydroxide, and the carboxylic acid is going to donate one of its hydrogens. Where in this case, we see that the carboxylic acid has lost its hydroxide, and the amine has formed has given up one of its hydrogens to make water as a byproduct. And that's it. You made it. That's all of S2, and there's a lot of material in S2, but hopefully this jogged your memory. I really hope I helped you in your journey for your Chem IB exam review. If you made it this far, thank you for watching. Stay quick and keep your melting point high on these exams. And if I helped you and you want to support me, consider liking, sharing, or even subscribing. That'll do it for now. Have a good night, or good morning, or good afternoon.